Hello, everyone. My name is John Aycock, and I am here to talk about nearly overconvergent modular forms. Okay, so for some motivation for why we might care, we want to maybe study the zeta function of a CM field. And what we're going to do is we're going to view the input to the zeta function as a Hecke character rather than as a number. And when we do this, we actually get something called Damerel's formula, which relates this value, zeta k of chi, to the sum over the CM points of some Eisenstein series of weight chi evaluated at these CM points. So there are some constants that come up, which is why this is listed as approximately equal to instead of just equals. But this is really tightly controlled by this value over here. And in fact, there are some differential operators, which I'm going to call nabla sub sigma, that we can use to relate these different e chi's. So for a different character, you can actually see you can actually get there sometimes using this differential operator. And for p-adic Hecke characters, which might not be finite order, which might involve kind of the norm happening, we can just interpolate these differential operators, and that allows us to interpolate the values of zeta k at different Hecke characters. This is done by Katz over the ordinary locus, and in fact, the thing that's an issue is that these CM points might not be in the ordinary locus, and in fact, if the prime p splits, then you get it, then you get this in the ordinary locus. But if the prime p is ramified or inert, then these CM points are actually outside of the ordinary locus for sure. And this is actually also able to be mimicked for other L functions as well. So you can do this for the L function of a modular form. This is done by Bertolini, Darmon, and Prasanna from 2013. So this is not the only way that you can use these CM points to actually find the values of a zeta function and these differential operators. So our main theorem is about these differential operators, and what we're going to do is we're going to state it in terms of Hilbert modular forms, because that's the space where I proved it, and then we're going to show it to you in terms of just classical elliptic modular forms for f equals q. So the main theorem says if we fix a totally real field f and a p-adic field k that splits f, so what this means is that k is just some finite extension of qp that contains f inside of it, and there are other things that happen that are important, but it's kind of an auxiliary field involved here. The theorem is that for each of the embeddings from f into k, and any positive kind of power, we're going to get a differential operator called nabla sigma to the k. It acts on families of nearly overconvergent Hilbert modular forms, and it does a couple of things. The first thing it does is it preserves overconvergence. So what this means is that it's actually defined over the entire modular curve and not just over the ordinary locus as Katz did it. It's going to raise the weight of each form in the family by this 2k sigma. So kind of each nabla sigma raises the weight by 2 sigma, and we're going to do that k times. That's where this nabla sigma to the k is going to come from. It's going to raise the type of each form in the family by k. So the type kind of tells you how far away am I from actually being overconvergent rather than just nearly overconvergent. And so we're applying this differential operator k times, so we think of this as raising the type of each form by k. One final thing that's important is that if you have two different embeddings, sigma and tau, then these nabla sigma and nabla tau are going to commute with each other, and that's going to make their powers commute with each other as well. For simplicity, we're going to do this for elliptic modular forms. And one other thing that we should note before we move on is that these differential operators, these nabla sigma to the k's, these are the p-adic analog of the Maas-Shimura operators. And these are operators that were used to study algebraicity, and they're kind of an Archimedean construction, but these are a p-adic construction that are kind of supposed to be analogous in that kind of a way. So The kind of layout of the talk is going to be, we're going to talk about, well, what is a modular form? And then what is a nearly overconvergent modular form? And then we're going to kind of prove this theorem out of there. So a lot of the work is going to be spent trying to figure out, well, what is a nearly overconvergent Hilbert modular form, or in this case, just elliptic modular form. And then once we've done that, we can prove the theorem fairly quickly from there. So we're going to view modular forms in the way that Katz does. And this is mimicked for other types of automorphic forms, notably Hilbert modular forms. This is what we use to prove the theorem. But we're just going to talk about modular forms in this case. So a modular form, in the view of Katz, is an algebraic function. F of e omega is going to give us a number. It has two inputs, e and omega. This first input, e, is an elliptic curve with level structure. And this second input, omega, is a non-vanishing holomorphic differential on E. We can view this as maybe an element of the cotangent bundle, but I'm going to say a non-vanishing holomorphic differential. And if E and omega are defined over some ring R, these are kind of algebraic constructs. If they're defined over some ring R, then f of E omega should be a number in R in particular. So if these are defined over z adjoin 1 over p, for example, then only p's are allowed in the denominators. But if they're just defined over c, over the complex numbers, then you actually get a complex number out. You might get something fully complex. So a modular form usually has a level and a weight. The level is kind of already baked into this level structure up here with input 1. Excuse me. But the weight k is going to be some sort of homogeneity property. And it's going to say, well, if I scale my holomorphic differential by some unit, if I ask what is f of e comma lambda omega, then I'm actually just going to scale my output by a power of that unit. And if f has weight k, then this is going to be lambda to the minus k is going to be the power that comes out. So we have a level, we have a weight. This is all very nice. So taking this a little bit further, these pairs e comma omega are actually points on what's called a frame bundle. And this frame bundle has an action of the units. So this frame bundle is supposed to be, it's a fiber bundle, and the points of the base are these elliptic curves with level structure. There are these e's, and each fiber is supposed to give you a point on the fiber is supposed to give you a frame for a certain line bundle. And so in fact, we have an action of R cross. If you have a unit in a ring, and this point is defined over the ring R, then you can actually scale that element by that unit by just scaling the holomorphic differential, by scaling the frame. This is going to mean that it forms a torsor for the group GM, the multiplicative group. So GM of R is going to be R cross over the moduli space of elliptic curves with level structure. And a Katz modular form is just a function on this torsor. And if it has weight k, then it has this homogeneity property. If I act by lambda on f, lambda being some unit, what that's going to do is it's going to kind of undo the action of lambda on the input. So since a lambda would scale omega, we're going to kind of unscale omega by lambda. And then that's going to pick out a power. So because lambda omega is going to give us lambda to the minus k out front, lambda inverse omega is going to give us lambda to the k out in front. So this is kind of this is the same homogeneity property from the last slide, but it's viewed kind of, it's slightly modified. And the ring of modular forms, so all weights of modular forms all together, is going to be given by all functions on this torsor. And you can kind of project each function to be a sum of functions of these homogeneous properties, kind of like a polynomial is the sum of homogeneous polynomials. So if we want all weights there, we just take the ring of modular forms, and these are just all functions on this torsor. So this is entirely an algebraic construction. And what we're going to do is, instead of kind of analytifying it and talking about modular forms over C, we're going to talk about overconvergent modular forms, which are a very p-adic kind of sense of object. So the first thing that we're going to do is we're going to formally complete this frame bundle. So all this really does is it says, okay, take all the functions that I have and just take p-adic limits of them and add them in here. We're just going to p-adically complete this ring. We're going to get p-adic limits of these functions. And it's important that all of the weights are present when we do this. It's important that we use the entire ring of functions on the frame bundle, the entire ring of modular forms when we do this, because there are Cauchy sequences, p-adically Cauchy sequences of modular forms whose weights are varying the whole time. So you can actually show that these weights should vary p-adically as well, but you can have the weights varying. You don't just have to end up with kind of a constant weight eventually. You actually can keep varying the weights and keep the weight going to infinity, for example, in a very specific way to get a nice p-adically Cauchy sequence of modular forms. And once we have formally completed, or maybe taken the rigid analytic fiber, which is a little bit easier to think about, we can make kind of two subspaces of the moduli space of elliptic curves. The first one is the ordinary locus. It's called X-ord, and it's the moduli space of ordinary elliptic curves. So this depends on the P that we've chosen, but if for our chosen P that we've p-adically completed this, we get this ordinary locus. And then we have also this slightly bigger moduli space, X of V. This is an overconvergent locus. And I like to think of it as the moduli space of quote unquote ordinary enough elliptic curves. This is in a very specific sense. This is related to the Hasse invariant, and this V is kind of a variable. It goes between 0 and 1, and it tells you how supersingular am I allowed to be in order for me to still count as being in these overconvergent locus. And what we're going to do is we're going to say, well, an overconvergent modular form, well, we can take any of these functions on this formally completed frame bundle, but in fact there are more. We can take a natural formal subtorsor, which exists over some overconvergent locus, and this is going to kind of allow us to have Nebentypus at P, which is sort of counted as part of the weight. And these overconvergent modular forms are functions on some formal subtorsor of this formally completed frame bundle. So not just p-adic limits of functions, but also you can kind of twist them by small enough characters with small enough Nebentypus at P. So we're going to have a couple of pictures coming up next. So we have the modular curve, and I'm also going to have a picture of the ordinary locus and of the overconvergent locus, this X of V. So because our modular curve is sort of an algebraic curve, you should think of it as one-dimensional over C rather than over R. So it's really kind of looks like a surface rather than a curve. So I've drawn just kind of a surface here. The ordinary locus, what we're going to do is we're going to take out all of the supersingular elliptic curves, and as it turns out, this is just going to be, there's going to be a finite number of disks, and each of these disks is corresponding to some some supersingular elliptic curve. So all of the supersingular elliptic curves live on these red circles, and what we do for the ordinary locus is we just take them out. So the rest of the curve is fine. These are ordinary elliptic curves, but the supersingular ones we're taking out. And the overconvergent locus, we should think of as, well, we've taken out all of these supersingular elliptic curves, but we actually want to put a little bit back in. So we want to give a little bit of these disks back in, and so we do. So these green circles are the pieces of those disks that we already took out for the ordinary locus. You can see the green circles are kind of the outside of these red circles. But then inside of these, we still have some things that we take out. We still don't have the entire modular curve that we started with, but we have a little bit more than just the ordinary locus. So what we're going to do is we're going to kind of switch gears. We talked about nearly overconvergent, we talked about overconvergent modular forms, algebraic modular forms, and then overconvergent modular forms. Now we're going to talk about nearly algebraic modular forms, and then nearly overconvergent modular forms. And we're going to start with these nearly algebraic modular forms. So it's going to be an algebraic function, f of e omega 1 omega 2 equals some number. And again, this is just like Katz modular forms, except you kind of added an extra little bit of data. So our first input is still e, an elliptic curve with level structure. Our second input, omega 1, is the same as omega was before, but there's two omegas now. So I call it omega 1 instead. So omega 1 is a non-vanishing holomorphic differential on E. And we're adding a third input, omega 2, which is a non-vanishing but not holomorphic differential on E. And the idea behind this is that this pair, omega 1, omega 2, is supposed to form a basis for the de Rham cohomology of E. So not just omega 1 forms a basis for the cotangent bundle of E. We want the de Rham cohomology, which is rank 2. So we need two elements in our basis, and the first one is going to be holomorphic, and the second one can be anything else, as long as together they form a basis. And we're going to have a little bit more information in the weight. We're going to have weight k minus s comma s. If for all a and d being units, if we scale the first element by a and the second element by d, then we're going to have this homogeneity property. And a comes out with the power s minus k, which is negative k minus s. And d comes out with the power negative s. So we kind of have, if we scale the entire basis by some single unit lambda, then we're going to end up scaling the whole thing by the whole output by minus k, by lambda to the minus k. But we kind of are splitting it out in two different spots this way. So these triples, this e omega 1 omega 2, these are going to be points in something that I like to call a filtered frame bundle. So the omega 1 comma omega 2 is a special type of basis for the de Rham cohomology, where the first one is in kind of a one-dimensional subspace. And that's what I mean by it's filtered. We kind of have a filtered two-dimensional vector space. The first element of the basis is in that one-dimensional subspace. The second element just can be anywhere else it wants. This is a torsor for the group of upper triangular 2x2 matrices. If you act on omega 1 comma omega 2, if you think of these as vectors, you act on these by an upper triangular matrix, well, you might scale omega 1, but it's still going to be in its same kind of subspace that it spanned already. And omega 2 can change. It can move somewhere else in this two-dimensional vector space, even though omega 1 is not. As long as it stays, since these are invertible matrices, this is going to stay a basis. We are going to formally complete the functions on this filtered frame bundle to get the p-adic limits. We're going to find some natural formal subtorsor to this, and the functions on that natural formal subtorsor, which live over an overconvergent locus, those are going to be our nearly overconvergent modular forms. So all of this is just like in the overconvergent case. We just have this extra little bit of data where we have the entirety of the de Rham cohomology trivialized instead of just the cotangent bundle. Okay, so this is what a nearly overconvergent modular form is. So what do we need to do? Well, now that we know what a nearly overconvergent modular form is, what we want to do is we want to find what are these differential operators, and we want to find how are we going to interpolate them. So the differential operators come from a Gauss-Manin connection. So if we call the relative de Rham cohomology H, this just says that the fiber over any point in the moduli space is the de Rham cohomology of that elliptic curve. We get a Gauss-Manin connection, which I'm going to call nabla, and it takes a section of H and it gives you a section of H tensor the cotangent bundle of X. The idea is that if you feed it an element of the tangent bundle, if you feed it a direction, this is going to give you kind of a partial derivative of a section of H in terms of a section of H. That's what, you can think of this as kind of like a generalization of the gradient, but instead of functions being taken the gradient of, we take the gradient, we take the gradient of sections of this vector bundle. And using the Leibniz rule, we can kind of, we can extend this to the symmetric powers of H. And the idea is that you'll differentiate the first element and leave the rest alone. Then you'll differentiate the second element and leave the rest alone. Then differentiate the third element and leave the rest alone. And then add them all up just like you would with the product rule. And this gives you some thing that's analogous to the gradient still, but it acts on sections of sim k of H. And the functions on the frame bundle of this Theorem cohomology bundle are actually elements of these symmetric powers sim k of H. So if we collect all of these, we actually get just a differential operator, a connection that goes from just functions on this frame bundle to functions on the frame bundle tensor omega 1 x, tensor this cotangent. And this is going to be a connection on a GL2 torsor, and we are going to formally complete it. So we get a connection that kind of acts on these p-adic limits. Okay, now in order to interpolate these connections, the main ingredient is that connections on torsors can be restricted to open subtorsors. So we have a torsor, we have a connection on a GL2 torsor, and we want an open subtorsor, and this kind of filtered frame bundle is a subtorsor, but it's actually not open. And that's a little bit of an issue, but then you see that it's open mod p to the n. Once you kind of base change to z mod p to the n, then this filtered frame bundle becomes open. And once you kind of collect these, that's going to be enough for a connection on its formal completion. Not necessarily algebraically, but on its formal completion, that's enough. So now we have this connection on its formal completion, and this is going to be our differential operator. But this is only actually going to work on kind of modular forms of trivial nebentipus at P. And so our last step is going to be to restrict again to this natural formal subtorsor. Remember, there's a natural formal subtorsor in the overconvergent case that allows us to give it kind of nebentipus at P. And this last one is open, so we don't have to do this kind of rigmarole that we did for the first one. And that's the construction. That's the entire proof of the theorem. Is basically 9 slides on what is a modular form, 1 slide on what is this differential operator, how do you make it, and 1 slide on how do I interpolate this. So that's my talk, and I hope you enjoyed it. Thank you.